launch Alliance Atlas V rocket.
Mach 1, execute, and we have an indication of spacecraft separation.
Good evening. I'm Andrea Lenhoff. I'm a systems engineering lead at ULA and your host for tonight's Atlas V USSF-12 launch for the United States Space Force Space Systems Command. I'm here at ULA's Atlas Spaceflight Operations Center at Cape Canaveral Space Force Station in Florida. Liftoff is scheduled for 6 p.m. Eastern, though we do have a 2-hour window available today. In addition to watching our webcast, you can also follow live mission progress at ulalaunch.com. The count is currently in a 30-minute planned hold. We have 2 planned holds in our 7.5-hour launch count, which give our team additional time to resolve any issues prior to entering the terminal count. At this time, the team is not working any issues and we are proceeding towards an on-time liftoff. Today's ascent to geosynchronous orbit is more than 6 hours, so we'll wrap up about 25 minutes after liftoff. Stay tuned after liftoff to hear more about Wide Field of View from U.S. Space Force's Colonel Heather Bogsty and Millennium Space Systems CEO Jason Kim. Before we continue, let's check in on today's weather forecast with Space Launch Delta 45 Weather Officer Will Ulrich.
Thanks, Andrea. Good things come to those who will wait. That's the saying, right? Well, unfortunately, it looks like we're going to have to wait a little bit longer as Mother Nature isn't entirely cooperating right now. My colleagues at the 45th Weather Squadron are actively evaluating those 10 lightning launch commit criteria to ensure we keep that rocket safe from both natural and rocket-triggered lightning. And one of those rules, the attached anvil cloud rule, is currently being violated. However, there are signs that those clouds are beginning to clear over the pad, and we will be in a go situation just before T0. But we'll continue to evaluate those clouds all the way up until the final few seconds of the count. Now, a live look at satellite imagery behind me shows those widespread clouds cover across the spaceport. But the deepest clouds, the strongest showers and thunderstorms are well west of Complex 41. And the clouds that you see over Cape Canaveral right now are beginning to thin. So that's why we're very confident in going into today's opening of the window, and we do look good. Jessica Williams just gave her final weather brief at L-30 minutes and gave a 60% chance of go or 40% chance of no-go conditions due to the cumulus cloud and attached anvil rules. Now, although Mother Nature isn't cooperating right now, we do expect her to cooperate here shortly, and we should be good to go at the opening of the window. Andrea, back to you.
Thanks, Will. Wind can play a critical role on launch day. ULA has a team of engineers making sure we maximize our launch opportunities with real-time wind monitoring and trajectory updates. To learn more, we spoke with Robert Olson.
I'm Robert Olson. I work at the Structural Dynamics Group here at ULA, and I'm responsible for the execution of operations here in the Denver Winds Room. We call it the Winds Room because we're monitoring the balloons that are released from the launch site, and they're measuring the winds aloft for us. And as part of that, we develop a steering algorithm for the vehicle to steer into the wind to minimize vehicle responses. And we're also verifying that the vehicle is structurally capable and can control itself flying through the wind. The team of engineers shows up here about 4 hours prior to launch. We have our first balloon release. We're trending the winds aloft conditions on launch day. And for each of those balloons, we see, is the vehicle structurally capable and can it control itself flying through those winds aloft? And what are the performance impacts from flying through those winds aloft? It's critically important for these low margin, high performing type of systems that we have a very deep understanding of exactly what the vehicle is going to experience. And in so doing, we're increasing our reliability and the confidence that we have in what the vehicle is going to experience. And we're going to ensure that the vehicle is not going to fail in the very dynamic lower portion of the atmosphere on its way to orbit. What is unique about this operation here in the Winds Room as well is that we are extremely agile in what we're doing because we have the capabilities to adapt to later balloons in the air and still meet our timeline for whatever T0 the entire launch team is working. It's very important for us here to balance reliability and launch availability. Reliability would be having the most amount of margin possible and protecting the vehicle in that way, while that would be in direct conflict with being able to launch at any given time. So we're balancing that here with the way that we operate with the balloons. We have many balloons in succession, very close to liftoff, and that allows us to provide that balance of launch availability and reliability.
Just as we went on air, the hold was extended. We will be unable to enter terminal count as the appointed time at 6:00 p.m. Eastern liftoff time. ULA is launching USSF-12 for the Space Force's Space Systems Command. Let's learn more from Government Mission Integration Manager, Lieutenant Paige Harrison.
USSF-12 features 2 satellite payloads, the Wide Field of View Testbed as well as the USSF-12 Ring. Atlas V will deliver both spacecraft directly to geosynchronous orbit, approximately 22,000 miles or 36,000 kilometers above the equator. The forward payload, Wide Field of View, is a testbed spacecraft that informs the next-gen overhead persistent infrared program, the successor for the Space-Based Infrared System program, or SBIRS for short. Designed to provide a resilient space-based global missile warning capability against emerging missile and counter space threats. Wide Field of View's primary mission is to explore future missile warning algorithms with data collected in space. The aft payload is a propulsive ESPA called the USSF-12 Ring. This ring is a classified mission to demonstrate future technology for the Department of Defense.
For today's launch, ULA is using an Atlas V 541 rocket. This is the 94th Atlas V launch and ULA's 151st launch. Produced in ULA's 1.6 million square foot production facility in Decatur, Alabama, the Atlas V Common Core booster is powered by an NPO Energobosch RD-180 engine. 4 Northrop Grumman solid rocket boosters provide additional thrust at liftoff. The Centaur second stage is powered by an Aerojet Rocketdyne RL-10 engine. The 2 spacecraft are encapsulated in a 5-meter diameter payload fairing produced by Beyond Gravity in Decatur, Alabama. These rocket components travel from Alabama to Cape Canaveral on ULA's rocket ship. Once in Florida, a series of events lead to today's countdown. We're here outside the Vertical Integration Facility, or VIF, at Space Launch Complex 41, where we're about to roll the Atlas V on the Mobile Launch Platform, or MLP, to the pad. Before we do, let's take a look at how we stack this rocket. Our process began with lifting the 107-foot or 33-meter booster onto the MLP. Then the team mated the SRBs to the booster, followed by the transportation and lift of the Centaur into position atop the Atlas V booster. Finally, the payload fairing with both spacecraft already encapsulated was mated to the Atlas V rocket. With the rocket fully assembled, we now transition to the final countdown procedure by rolling it from the VIF to the pad. To complete this move, 6 components are used for the 20-minute trip, which spans about 1/3 of a mile. The MLP weighs approximately 2 million pounds, supports the rocket, and contains air conditioning, electrical, and commodities lines. The undercarriages bear the weight of the MLP in the rocket. The Atlas V rocket stands 196 feet, or about 60 meters, and weighs 775,000 pounds, or more than 350,000 kilograms fully fueled. With the rocket on the pad, the launch team transitions to fueling and other final preparations. We have an update on the weather. I'm going to hand it back to Will for a status.
Hey, Andrea. Just wanted to give a quick update because I just heard from my colleagues at the 45th Weather Squadron over at the Morrell Operations Center that the estimated clear time on that one rule that we've been monitoring, the attached anvil rule, is going to last a little longer. So we are going to have to eat into today's window. And those clouds that you see over the spaceport are remaining a little bit thicker than we originally anticipated. So that attached anvil cloud rule is not expected to clear until 6:15 p.m. local. Now, we still anticipate going into a go situation here shortly thereafter. So we still have plenty of time within that 2-hour window to get today's launch off the ground. Back to you.
ULA's Atlas V 541 rocket is launching both spacecraft to geosynchronous orbit. Let's learn more about today's flight.
The RD-180 main engine and 4 solid rocket boosters ignite to lift the Atlas V rocket away from the pad. Together, the main engine and SRBs generate a combined liftoff thrust of 2.25 million pounds, or about 10 meganewtons. The Atlas V reaches Mach 1, the speed of sound, at 35 seconds. 1 minute, 48 seconds into flight, the first 2 GEM 63 solid rocket boosters are jettisoned. The remaining 2 are jettisoned about 3 seconds later. At approximately 3 minutes, 25 seconds, the rocket has climbed above the densest part of Earth's atmosphere, and the payload fairing is jettisoned. 4 minutes, 24 seconds into flight, propellant levels are depleted and the main engine shuts down. 6 seconds later, the Atlas Centaur separation system activates to release the booster stage. The rocket now weighs a little more than 5% of what it did at liftoff. At 4 minutes, 40 seconds, the first Centaur main engine burn begins. Following a 12-minute, 15-second coast, the second Centaur main engine burn begins. Within this sequence, the second burn is used to raise the apogee to a near geosynchronous altitude. 5 hours, 43 minutes, 54 seconds after liftoff, the RL-10 engine ignites for a final burn. Nearly 2.5 minutes later, Centaur completes its final engine cutoff following a guidance-commanded shutdown. The first of 2 spacecraft separations occurs at 5 hours, 49 minutes, 36 seconds, releasing wide field of view for the Space Force's Space Sensing Directorate. At 5 hours, 59 minutes, 3 seconds, Centaur releases the booster adapter. 6 hours, 5 minutes, 21 seconds after liftoff, Centaur releases the USSF-12 Ring spacecraft for the Space Systems Command Innovation and Prototyping Directorate.
ULA's Vulcan rocket is nearing its first flight. While we're waiting for a new T0, let's get an update on Vulcan.
Vulcan Centaur production begins with aluminum sheets, expertly machined to remove more than 2/3 of the weight, resulting in the structurally strong yet lightweight orthogrid panels that form Vulcan's propellant tanks. The panels are then bump pressed to form the curves required to complete the tanks. At the same time, rings, adapters, and other structural components are precision milled. Next, the aluminum domes, panels, and other structures that form Vulcan's propellant tanks are first cleaned and etched to a smooth, even surface, and then anodized to harden and prevent corrosion. Following an ultrasonic inspection, 5 completed panels for the liquefied natural gas, or LNG tank, are assembled and joined together using friction stir welding. Unlike traditional welding, where filler material is used to join components, friction stir welding uses a head to stir the metal of the two panels together as it moves down the seam. The resulting joint is stronger and produces a lighter weight, higher performing tank. The process is repeated to create the liquid oxygen, or LOX tank, followed by attaching domes to complete the tanks. Circumferential friction stir welding is then used to join the two propellant tanks that comprise the Vulcan booster. As production continues on the booster stage, stretch-forming gore panels for the Centaur's second stage propellant tanks is underway. The stainless steel gore panels are welded together to create the propellant tank domes. The gore welder is one of several highly specialized welding stations in the Centaur production process. Just down the aisle, Centaur 5's massive intermediate bulkhead is mated to its ultra-thin tank. Once both propellant tanks are welded, they're mated together to create the Centaur 5's second stage. Once the propellant tanks are joined, the 5.4-meter booster is sprayed with foam insulation before moving to final assembly. Twin BE-4 engines are hot-fired and then mated to Vulcan's thrust structure. With production complete, the booster makes its way onto ULA's rocket ship for its journey to the launch site. Meanwhile, at Cape Canaveral's Space Launch Complex 41, the water suppression system has been upgraded and tested, along with other modifications, including new, larger fuel storage tanks. In the Vertical Integration Facility, or VIF, platforms have been modified to accommodate the larger Vulcan rocket. Following the 8-day journey to Cape Canaveral, the booster is offloaded and transported to the VIF, where it is lifted onto the newly constructed Vulcan Launch Platform, or VLP. The first Vulcan booster then travels a third of a mile to the pad for testing, followed by 2.7 miles to the Spaceflight Processing Operations Center, or SPOC, for additional testing. This launch site testing culminates with another trip to the pad, where the LOX and LNG tanks will be filled and chilled to flight levels and temperatures.
The Space Force provided the artwork we see on today's payload fairing. Today's artwork includes projection of the world in the center as viewed from space, reflecting a wide field of view as seen through a wasp's eyes. Additionally, there are two black stars inside a red plume to represent the two space vehicle programs. In addition to monitoring the Anvil cloud rule, we are also monitoring wind. As we learned in the earlier video, a series of weather balloons has been launched throughout the countdown from the range weather station at the Cape to collect measurements of wind speeds and directions to determine if conditions aloft violate the controllability or structural loads on the rocket during ascent. The balloon data is transmitted to ULA engineers in Denver to select a steering profile that minimizes launch vehicle responses. ULA builds Atlas, Delta, and now Vulcan rockets in a 1.6 million square foot facility in Decatur, Alabama. Here's a look inside.
Successfully launching missions to every planet in the solar system, in addition to critical national security, science, weather, and communication satellites, ULA has established a long-standing industry reputation for reliability and orbit accuracy. While our rockets lift off from launch pads in Florida and California, the journey to space begins in Decatur, Alabama. At approximately 1.6 million square feet, ULA's production facility is an always-on workhorse where technicians simultaneously build components for Atlas V, Delta IV Heavy, and Vulcan Centaur rockets. Booster production begins when large aluminum plate stock is loaded into one of 4 double gantry skin milling machines, where aluminum is milled into patterns designed for building tanks and other components. This process helps reduce the original weight of each panel by 70%, while maintaining approximately 75% of the original material strength. After machining, skin panels are transported to the brake form and bump pressed into the precise curved radius required to create fuel tank barrel sections. Components made from aluminum require anodization to protect from corrosion. For this requirement, certain components, like skin panels, are first given a high-pressure wash and then dipped in a series of chemicals to complete the sealing process. Skin panels are then transported to the vertical friction stir welder, where they are lifted and forged together to form the barrel sections of the fuel and oxidizer tanks. Delta IV and Vulcan Centaur tanks are comprised of 5 skin panels, while 4 skin panels form the Atlas V tanks. Friction stir welding is a unique process accomplished by a pin tool, which applies frictional heat and stirring of the parent material to form a weld. This process only uses friction as the heat source and has no filler material, making an extremely strong welded joint. Completed aluminum barrel sections then move to the circumferential friction stir welder, where domes are welded to each end, completing the first stage fuel tanks. After pressure testing, which verifies the integrity of the welds, the next stop for booster fuel tanks is the spray-on foam insulation booth, or SOFI. This is where completed tanks are primed, then insulated to protect from the acoustics that occur at liftoff. Tanks then move to final assembly, where components like wiring and engines are added. In addition to the first stage, or booster stage, ULA's second stages are also built in Decatur. The factory has recently undergone a major reconfiguration, resulting in a new state-of-the-art Centaur V production line to increase the speed at which Vulcan Centaur second stages are built, assembled, and tested. The Centaur upper stages for Atlas and Vulcan are built using a thin stainless steel structure, making it the most efficient upper stage currently in use. To create the domes or bulkheads for Centaur's 2 tanks, gores, or pie-shaped sheets, are welded together. The bulkheads and tank skins are then assembled using a combination of spot and seam welds. Spray-on foam insulation, or SOFI, is then applied to the Centaur tank to provide thermal protection for the cryogenic fuels. Centaur's tanks are known as pressure-stabilized tanks because 90% of their weight and structure at launch is from the mass of the fuel and oxidizer loaded prior to liftoff. The Centaur tank then moves to final assembly, where engines, avionics, pneumatic, and propulsion systems are installed. At the end of the production journey, all systems on both the booster and Centaur are fully tested, and the stages are prepared for transport to the launch site. With testing and transport preparations completed, Atlas V, Delta IV Heavy, and Vulcan Centaur rockets exit the factory and roll about a mile down the road to a dock on the Tennessee River. Once loaded onto the RS rocket ship, ULA's specially designed cargo boat, the rockets begin the 8-day trip to Cape Canaveral Space Force Station, Florida, or the 23-day trip to Vandenberg Space Force Base, California.
The launch team continues to track both issues. Anvil clouds remain unacceptable for flight, and the most recent upper-level wind reading was red. Let's get an update from Will Ulrich.
Thanks, Andrea. The waiting game continues. First, let's talk about the attached anvil rule. Live look at satellite imagery right now continues to show upper-level clouds streaming over the spaceport. And those clouds, although they are thinning, they remain situated directly over Complex 41. So they're taking a little bit more time to get out of the way. With that in mind, my colleagues at the 45th Weather Squadron have updated the estimated clear time to no earlier than 6:30 p.m. this evening. So we're going to have to wait a little bit longer. Additionally, upper-level winds are currently unfavorable. And it's not that those winds are particularly strong, because at this time of year, winds are typically very light from the surface all the way through the upper portions of the atmosphere, but they are variable. So flight teams in Denver and with other units inside of United Launch Alliance are keeping a close eye on the changeability or variability of those wind speeds to ensure that the rocket makes the correct adjustments as it moves up into the atmosphere. So with that said, we're not going to go any earlier than 6:30 p.m., but the general trend is our friend as those clouds continue to thin and move out of the way. We'll provide an update as soon as I have one. Back to you, Andrea.
Thanks, Will. This May, ULA lifted the Boeing Starliner capsule for NASA, marking our 150th launch since our doors opened in 2006. Let's take a look at some highlights commemorating this milestone.
150. 150 consecutive launches. 150 consecutive successes. At ULA, 100% mission success is an achievement that both defines us and motivates us. As the industry's most experienced launch service provider, we continue to provide world-leading reliability, schedule confidence, and mission optimization. And we're proud to lead the way in space to expand what's possible on Earth. Our pride is built on the successful launch of 93 national security missions, 18 GPS satellites, 5 trips to Mars, 18 commercial missions, and 39 science and exploration missions. From low Earth to the most complex geosynchronous orbits and interplanetary trajectories, ULA is the only launch provider capable of delivering to any orbit, anytime. 30 Delta IIs, 23 Delta IVs, 12 Delta IV Heavies, 85 Atlas Vs, 150 flights using our trusted fleet of rockets built to the evolving needs of each and every customer. We've traveled 2,500,000 miles and delivered more than 1,400,000 pounds to orbit. Deliveries that have improved the way we live and work and provided a deeper understanding of our universe. All rockets are not created equal, and when it absolutely must get to space safely and on time, customers choose ULA. 150 glorious liftoffs, 100% mission success.
We often get questions about the various clock displays visible in the Launch Control Center, most notably the T count and the L count clocks. T simply stands for time and L for launch. The T count is a scripted time until T0. All of the launch vehicle countdown events are procedurally sequenced to T time. The L count is the total amount of time until launch, which is the T time plus the built-in holds. Built-in holds are placed at strategic points in the countdown. For instance, before cryogenic loading and before the terminal count and liftoff, and are contingency time that the team can use if needed to catch up in the event of a delay in countdown activities.
LC, LD, channel 1.
Go, LD.
LC, load contingency adjust file, adjust underscore AV094 underscore 07, SDLCRC 511 Delta.
Roger, AV094 underscore 07, 511 Delta. Flight control, LC. Go ahead, this flight control. You have a go to load contingency file, adjust underscore AV094 underscore 07, SDLCRC 511 Delta. And work.
We have another update on the weather. I'm going to hand it back to Will Ulrich for a status.
Hey, Andrea. It's like we keep pushing the snooze button waiting for tonight's launch, right? I have a little bit of an update from my colleagues over at the 45th Weather Squadron. Satellite imagery continues to show that anvil cloud sitting overhead, and this live shot that you see right now shows that anvil cloud perfectly over Complex 41, and unfortunately it just doesn't want to move. Now originally we were evaluating that cloud under the attached anvil cloud rule because it was attached to its parent thunderstorm. That thunderstorm has since dissipated, so we're now evaluating it under the detached anvil cloud rule. Unfortunately, that doesn't really change the status that we're in. We are in a no-go status for the detached anvil rule with an updated clear time of 6:45 p.m. So we still have at least another 15-20 minutes to go before we can start thinking about setting that new T0. So that's all I've got.
Atlas V launch of USSF-12. This visibility map shows when and where your best chances are to see the rocket as it launches from Cape Canaveral. While we are still waiting to clear the Anvil cloud rule, a new upper-level wind profile has been loaded into the Atlas V rocket's onboard computer, and the upper-level winds are now green. I'm going to toss it back to Will Ulrich for more details on the weather.
Hey, Andrea, that's great news about the upper level winds. Now that means all that we're left with is continuing to monitor the detached anvil rule. And I wanted to bring up GR Analyst, which is one of the tools that we use at the 45th Weather Squadron to evaluate current radar imagery. Now what you're looking at right now is called radar reflectivity, and it shows the cloud of concern at approximately 20 to 30,000 feet. This is that detached anvil cloud rule that my colleagues at the 45th Weather Squadron are actively evaluating. Now, the good news is that cumulus cloud is detached anvil cloud is beginning to dissipate. If I put it forward into time, notice how that cloud is gradually thinning out. And that's what we need to look for in order to get us out of that detached anvil rule. So I do expect an update from my colleagues here soon. We may be able to clear that detached anvil rule for much longer. And really, if we're green on upper level winds, we're not really concerned with anything else at this point. And I do think we have a shot to launch later today. Back to you.
We have another weather update. I'm going to send it over again to Will Ulrich.
Hey, Andrea. Just heard from my colleagues at the 45th Weather Squadron over at the Morrell Operations Center, and we are extending the no-go status on that detached anvil cloud rule for a little bit longer. And one of those reasons is because that cloud, though it is dissipating, it's still above the limit that we monitor to ensure that cloud does not pose a threat for rocket-triggered lightning. So the clouds that you see there over Cape Canaveral are moving in the correct direction. They are slowly moving from the west to the east, and even though they're moving very slowly, they're also dissipating at the same time. So long as we continue to see that trend, and we still have about an hour and 10 to an hour and 15 minutes left in the window, the trend is our friend, and we're hopeful that that cloud will get out of here in time so that we can launch just after 7 p.m. I'll provide an update as soon as I hear. Back to you guys.
LC, LD, Channel 1.
Go LD.
Please coordinate a new T0 with the range 231500Z.
Roger, 231500Z. ALC, LC.
Go ahead.
Please set the clock for 231500 T0.
Roger.
RC, LC.
RC on 1.
Please coordinate with the range, new T0, 23:15:000.
Roger. The countdown clock has been set for new T0 of 23:15 Zulu. Clock is at L-23 and counting.
Roger. All right, for a team, we'll pick up at L-16. CT1, start giving us a time max at that time.
LC, Net 1.
No RC.
The range has approved our new T0 time of 23:15:00T.
Roger. All right, team, T0 is approved. And we are counting.
L-23 minutes.
As you just heard, a new T0 has been set for 7:15 p.m. Eastern Time.
L-21 minutes.
We've created a short tour of our launch locations here in Cape Canaveral, Florida. Let's take a look around.
With missions launched to every planet in the solar system, as well as critical national security, science, weather, and communication satellites, ULA has established a long-standing reputation for reliability and orbit accuracy in the space launch industry. At our launch site in Cape Canaveral, Florida, the story begins with ULA's Atlas and Delta rockets arriving on the RS rocket ship. The rocket ship is a specially designed cargo ship used to transport rockets from ULA's 1.6 million square foot production facility in Decatur, Alabama. Rocket ship is large enough to carry a complete Delta IV Heavy rocket. That's 3 boosters, a second stage, and a payload fairing. Once loaded, rocket ship departs ULA's dock and travels through the Tennessee River, then onto the Ohio and Mississippi rivers, then goes out into the Gulf of Mexico. From there, the ship travels through the Atlantic Ocean, around the southern tip of Florida, and north to Port Canaveral. Rocket ship was designed with several features to ensure successful delivery, including the ability to adjust its draft for shallow water and rudderless steering, which minimizes the need to tug. Atlas V boosters are transported from the ship to the high bay in the Atlas Space Flight Operations Center, or ASOC, for final preparations. Delta IV boosters are moved to the Horizontal Integration Facility, or HIF, where they are mated together to form the Delta IV Heavy configuration. With final checks completed, the boosters are transported to the launch pad for Launch Vehicle on Stand, or LVOS. The 107-foot-long Atlas V boosters are brought to Space Launch Complex 41 and are hoisted into a vertical position using a crane and placed onto the Mobile Launch Platform, or MLP, in the Vertical Integration Facility, or VIF. Delta IV Heavy rockets are raised vertically by a fixed pad erector at Space Launch Complex 37. The fixed pad erector uses a single hydraulic piston to rotate the boosters 90 degrees inside the Mobile Service Tower, or MST. LVOS is followed by the addition of solid rocket boosters, and then the second stage. Next comes Wet Dress Rehearsal, or WDR, which is an end-to-end launch simulation, from fueling through spacecraft separation. Meanwhile, the ULA team is also working simultaneously to help the customer encapsulate their payload into the rocket's payload fairing. The encapsulated payload fairing is the final piece to be mated to the rocket. With the rocket stack complete, the spacecraft team tests all of the interfaces with the rocket and the launch pad. Once the rockets are completely assembled, final launch preps begin. For Atlas V rockets, launch countdown begins with moving the rocket from the VIF to the pad. The quarter-mile trip uses 6 components to complete the 20-minute trip. Weighing in at about 2 million pounds, the MLP supports the rocket and contains air conditioning, electrical, and commodities, while the undercarriages bear the weight of the MLP and rocket. 2 rail cars lead the move, with the payload van providing communication to the payload, while the ground van houses the ground support for the rocket. At the rear of the convoy, the portable environmental control system provides air conditioning to the payload and rocket. Finally, track mobiles provide the power to move the 3.5 million pound convoy. For Delta IV Heavy rockets, the process looks quite different. Approximately 9 hours before T0, final preparations begin as 40 hydraulic cylinders at pressures nearing 3,500 psi move the 10 million pound MST. It's first raised 8 inches and then rolled back. Delta uses a carriage transporter system, traveling at about a quarter mile per hour. It takes about 25 minutes to roll the MST to its launch position, 345 feet north of the Delta IV rocket. The Delta IV rocket stands 217 feet tall, or about 21 stories, and weighs more than 900,000 pounds fully fueled. On the day of launch, nearly 30 engineers and managers are polled for system status and readiness to proceed.
Status check to proceed with terminal count, Atlas Systems, propulsion.
This is the final status check before launch for all Atlas and Delta vehicle systems, ground systems, the spacecraft, and the U.S. Air Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants.
Range coordinator. Clear to proceed. Launch director.
Launch vehicle is ready to launch.
Mission director.
This is the mission director. You have permission to launch.
Proceeding with the count.
If the rocket is ready for flight and the weather is within the launch commit criteria, then polling will be completed and the team will have given the go for launch.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. There's ignition. And liftoff of the United Launch Alliance Atlas V rocket.
For a typical Atlas V flight, the main engine and solid rocket boosters ignite to lift the rocket off the pad. Shortly after liftoff, the rocket begins a pitchover to attain the proper flight path, minimizing the dynamic pressure the vehicle experiences during flight. Within the first few minutes of flight, the vehicle reaches Mach 1, the speed of sound, followed by jettison of the solid rocket boosters. About 4 minutes later, propellant levels deplete and the booster engine shuts down, followed by release of the booster stage. At various times in flight, depending on the mission, the vehicle jettisons its payload fairing. From there, the second stage will continue carrying the spacecraft towards its destination with planned engine starts and stops. Finally, Centaur will release the spacecraft in its target orbit to continue its journey.
LC, this is CRT.
We have an update on the weather. I'm going to hand it back to Will Ulrich for a status.
Hey, Andrea, some really good news. Those clouds that you see on satellite behind me continue to thin, and I just got word from the meteorologists over at the 45th Weather Squadron that we are now go for the detached anvil rule, and that means we're go on all Lightning launch commit criteria. So good news, we are progressing well towards that 7 p.m. liftoff time. All things are go from weather. Back to you guys.
LC, Channel 1.
Go LD.
Roger, sir. Load contingency adjust file. Adjust underscore AV094 underscore 08 with an SDL CRC of 97 Charlie Charlie.
Roger. Flight control LC. Go ahead, this flight control. Load contingency file adjust AV094 underscore 08 with SDL CRC 97 Charlie Charlie. Roger, and work.
L-minus 13 minutes.
And for the team, we will hold off on IFPS transfer to L at form that at L-minus 9 minutes.
Today's flight is dedicated to Dr. Vladimir Shabanov, Karl Thralkil, and Rochelle Wunderlich. Dr. Vladimir Shabanov was directly involved in the creation and modifications of rocket engines for much of the latter Soviet period, and has long been considered the father of the RD-180 engine, having directly supervised its design. This engine has successfully launched all Atlas III and Atlas V rockets, and USSF-12 is the 100th launch of an RD-180 powered booster. Not only was he an accomplished scientist, he was also well respected by his colleagues at ULA and by our customers. His personable nature made him approachable by all who interacted with him. Karl Thralkil began his career at the Rocket Ranch in September 1997. A veteran of the Delta II, Delta IV, Atlas V, and Vulcan programs, Karl was an inspector responsible for the integrity of our products, the safety of our team, and ultimately the satisfaction of our customers. Karl always demonstrated professionalism tinged with wit that kept all smiling with his jokes and antics. He never met a stranger. Rochelle Wunderlich began her aerospace career with Pratt & Whitney in 2001. She recently celebrated her 19th year of combined service with Pratt & Whitney and Aerojet Rocketdyne. Rochelle was an outstanding engineer that understood her products and her team. Her efforts at maintaining supplier quality were key to keeping the RL-10 flying successfully for nearly 2 decades. Earlier this year, she posthumously received the Palm Beach County Engineering Council Merit Award. She remains loved by many and will be deeply missed by all who knew her.
All communications switch to channel 1. All personnel and visitors remain in present position until launch. Maintain operational silence in the LCC. L-minus 10 minutes.
Terminal count briefing. If a condition exceeds a launch constraint anytime after a terminal count status check, the observer shall announce hold on channel 1, identify their station, and briefly state the reason for the hold. Flight control, perform launch on time verification. Flight control. Roger. OSM, place SRB ignition SMA switch in enable position.
LC, this flight control.
Go.
Contingency file adjust underscore AV094 underscore 08 with SDL CRC 97 Charlie Charlie has been verified and loaded into the Inca.
Roger. LC.
LD on channel 1.
Permission to enable IFPS.
Roger, proceed.
L-minus 9 minutes.
Flight control, enable WFOV IFPS report complete.
This is Atlas Mission Control at T-minus 4 minutes and holding. The team is still working towards a 7:15 p.m. Eastern launch.
Ignition SNA switch and enable position.
SRB ignition enabled.
Box 2, verify CISA purge flowing GN2 to the CISA.
Verified.
OSM, verify the FCO, ROC, and OSM whole fire switches are in the proceed position.
Ready to proceed.
RLM, verify redline monitor and vent table are in the correct configuration for terminal count. Verified. RC, verify solid radiation acceptable for launch.
Verified. WFOV IFPS enabled.
Roger. CRTD, begin telemetry verifications.
LC Sierra TD, we can confirm 33.04 volts.
Roger. And flight control looking for your launch on time verification.
Roger. In work.
L-minus 8 minutes.
We remain in the hold as we continue towards liftoff. In a few minutes, launch conductor Scott Barney will pull the launch team for the final go to pick up the countdown. 29 engineers and managers are pulled for system status and readiness to proceed. This is a final status check for all Atlas vehicle systems, ground systems, spacecraft, and the U.S. Space Force Eastern Range. The vehicle system readiness poll includes electrical systems, hydraulics, pneumatics, propulsion systems, flight control, and propellants. Let's listen in as Scott Barney performs the final polling.
All steps are complete prior to the status check. LC, switch to ready position.
L-minus 7 minutes.
Status check to proceed with terminal count. Atlas systems, propulsion. Go. Hydraulics. Go. Pneumatics.
Go.
LO2. Go. Water. Go. Centaur systems, propulsion.
Go.
Pneumatics.
Go.
LO2. Go. LH2. Go. Has gas. Go. Electrical systems, airborne.
Go.
Ground. Go. Facility.
Go.
RFFTS.
Go.
Flight control.
Go.
GCQ.
Go.
Operation support.
Go.
COM.
Go.
Umbilicals.
Go.
ECS.
Go.
Redline monitor.
Go.
Quality.
Go.
Ops safety manager.
Go.
ULA safety officer.
Go.
Vehicle system engineer.
Go.
Anomaly chief.
Go.
Range coordinator.
Clear to proceed.
Launch director.
Standby. Awaiting POLs for winds.
Roger. I will hold prior to coming out of the count. And LD, LC, that one.
LD.
Are you expecting to get a clear in the next minute and a half?
Yes, we are. This is the LD. Launch vehicle is ready to launch.
Roger. Mission director.
Mission Director, you have permission to launch.
Proceeding with the count. ALC, verify T0 is set for 23:15:00.
Verified.
CRTD, verify WFOV is configured for launch.
WFOV is configured for launch.
Polling is complete. The ULA launch team and the Space Force mission director are go for launch. From T-minus 4 minutes until launch, you will be listening to Scott Barney and his team performing the final steps in the countdown procedure. Several critical activities occur in the final minutes before launch, including verifying fuel tank levels and pressures in the booster and Centaur and arming the flight termination system. At T-minus 25 seconds, you'll hear Go Atlas, Go Centaur, Go USSF-12. This is a final status check of Atlas, Centaur, and USSF-12 readiness. At T-minus 3 seconds, the main engine ignites, followed by ignition of the solid rocket boosters. Then after seeing the Atlas V lift off the launch pad, you'll begin hearing flight commentator Patrick Moore providing ascent data as the rocket makes its way to orbit. This is Atlas Mission Control at T-minus 4 minutes and holding. We anticipate releasing the hold in just a few moments.
2, 1, mark. 359.
Transferring ring to internal power.
Roger.
355.
Ground pyros enabled.
The countdown clock is resumed and we are go for launch at 7:15 p.m. Eastern. With liftoff approaching, we're going to raise the volume on our launch team so you can hear the final preps.
.330.
Atlas hydraulics at flight pressure.
Minutes.
Securing LZ topping.
Atlas tank to flight pressure.
250.
FPS internal.
.159.
Vehicle internal.
155.
Launch sequencer start.
150.
Securing Centaur LH2.
Securing Centaur LO2.
140.
Launch enabled.
137.
T-minus 90 seconds. The launch vehicle, payload, ground systems, and eastern range are go for launch.
Launch. Ring is configured for launch.
120.
OCU's armed.
SCS count started.
115.
Reduce ECS for launch.
Roger.
110.
Vent valves locked.
T-minus 1 minute.
Range green.
Seconds.
Stable at step 3.
Verify ECS reduced for launch.
Verified.
25.
Status check.
Go Atlas.
Go Centaur. Go USSF-12.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have engine ignition and liftoff of the United Launch Alliance Atlas V rocket, carrying USSF-12 for the United States Space Force.
On the pitch over program, body range look good. NPU's gone to closed loop. System response looks good. Now 20 seconds into flight. Atlas is now completing the pitch over maneuver. Body rates continue to look good. RD-180 is throttled down slightly to partial thrust. Response looks good. Now 36 seconds into flight. Atlas V is now passing Mach 1. RD-180 continue to look good in partial thrust mode. Seeing good chamber pressures on all SRBs. And 49 seconds into flight, max Q, maximum dynamic pressure. RD-180 engine operating parameters continue to look good. SRB chamber pressures also look good, now passing 1 minute into flight. RD-180 now throttling back up to full thrust as expected. Chamber pressures on the SRBs continue to look good. RD-180 engine operating parameters also look good. Now 1 minute, 23 seconds into flight, approximately 3 minutes now remaining in the boost phase of flight. And at this point in the flight, Atlas V now weighs just 1/2 of its liftoff weight. And see SRB chamber pressure is tailing off now. And we have SRB burnout. 1 minute, 45 seconds into flight. RD-180 engine operating parameters continue to look good. And we have jettison of all 4 solid rocket boosters. Vehicle has gone to closed loop steering. Body rate responses look good. Just past 2 minutes into flight now. RD-180 throttling down slightly as expected. Engine operating parameters continue to look good. And 2 minutes now remaining in the boost phase of flight. Atlas V is now 50 miles in altitude, 78 miles downrange distance, traveling at 5,000 miles per hour. 2 minutes, 40 seconds in. RD-180 engine operating parameters continue to look good. Vehicle body rates looking good throughout boost phase. And the Centaur reaction control system is now pressurizing to flight levels. System response looks good. Coming up on 3 minutes into flight. RD-180 now throttling to maintain a constant 2.5 G acceleration limit, seeing good response on the RD-180. Body rates continue to look good throughout boost phase. Now passing 3 minutes, 20 seconds into flight. Approximately 1 minute now remaining until BECO. And we have good indication of payload fairing jettison and CFLR deck jettison. Vehicle's now throttled back up slightly. Engine response continues to look good. And RD-180 now throttling to maintain a constant 4.6 G acceleration limit in preparation for BECO. And we have boost phase chill down. Passing 4 minutes into flight. Vehicle systems all continue to operate nominally throughout boost phase. Body rates continue to look good. RD-180 engine operating parameters continue to look good as it maintains that acceleration limit. Standing by for BECO shortly. And we have BECO booster engine cutoff, standing by for stage sep. And we have good indication of stage separation. We have pre-start on the RL-10, standing by for ignition. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rates look good. Centaur's gone to closed loop steering. Body rates continue to look good. Now 5 minutes into flight. RL-10 chamber pressure continues to look good. Body rates look good. This first burn of today's mission will last approximately 6 minutes, 18 seconds.
This is Atlas Mission Control at T plus 5 minutes and 14 seconds. We just heard flight commentator Patrick Moore confirm the successful completion of the early phase of today's flight, and all systems continue to operate.
View will really help shape how we implement our architecture moving forward and get after that threat. We are working with the Space Development Agency and the Missile Defense Agency in a combined program office to have an integrated missile warning architecture that will soon pivot away.
Body rates continue to remain very stable throughout the coast. And in approximately 3 minutes, the Centaur will ignite to begin the second burn of today's mission. 23 seconds prior to ignition, RL-10 will begin the fuel and oxidizer pre-start sequence. This burn will last approximately 5.5 minutes. Centaur systems all continue to look good. And now approaching the final 2 minutes of the coast. "100 seconds now remaining until mess 2.
We're just a couple minutes away from our next mission event, second Centaur main engine start, or mess 2. Let's get back to the mission. Once again, here's Patrick Moore.
Body rates continue to look good. LOX and LH2 tank pressures have remained stable throughout the coast. And tank pressure is now beginning to increase in preparation for the burn. Just under 1 minute now remaining until mess 2. Tank pressure is continuing to increase in preparation for the burn. 30 seconds to engine ignition. Centaur's begun the pre-start sequence. We have good pre-start on LOX and LH2 and standing by for ignition shortly. We have ignition and full thrust on the RL-10. Chamber pressure looks good. Body rate stamping out nicely from the startup transient. This burn will last approximately 5.5 minutes. Centaur's gone to closed loop steering. Body rate responses continue to look good.
This is Atlas Mission Control at T plus 23 minutes and 38 seconds. Patrick Moore just reported successful start of the second of 3 Centaur engine burns. The 2 spacecraft are scheduled to separate from Centaur in a geosynchronous orbit in about 5.5 hours. I'd like to thank Patrick Moore for his participation in today's show, as well as Will Ulrich from the Space Launch Delta 45 weather. You can stay updated on today's long ascent to orbit with ULA's live blog at ulalaunch.com or join the conversation on Twitter and Facebook. I'm Andrea Lenhoff. Thank you so much for joining us tonight, and I'm really glad that we were able to see this rocket get off the pad. But before we sign off tonight, let's take a look at that liftoff that occurred at 7:15 p.m. Eastern Time. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We have engine ignition and liftoff of the United Launch Alliance Atlas V rocket, carrying USSF-12 for the United States Space Force.
Pitch over program, body rates look good. NPU's gone to closed loop. System response looks good. Now 20 seconds into flight.